This video is going to talk about a special type of predictive analytic model that gets used a lot in marketing applications. So this model is sometimes called a scoring model. So a scoring model is used to predict the future behavior of some customer based on whatever information I have about that customer. So one example of this could be programmatic advertising, where if I were to go to a media site and get, call up a web page, there may be many slots for banner ads. In the split second between, me calling up the page and the page rendering, a series of auctions take place where advertisers place bids on my attention. And so who, or in other words, who gets to show their ad in the banner ad spot. Now, that the auctions get informed by how likely I am to buy the product, which is from a scoring model. So the way we build these scoring models is that we identify some proxy behavior. So I call proxy behavior, maybe I tested a bunch of ads yesterday, okay? And so I'm going to try to predict responses to the ad I had yesterday using the information that I had available at the time of the bid in a predictive model and use that to inform my bids. So the way I like to think about this is if this is time, so time is like this, I turn back the clock and there is going to be some point in the past that I refer to as now. And that now is when the decision was made to contact the person or not. All right. So after this decision was made, we're going to assume that we're using all of the people who got exposed to the contact point, and I observe their response. Their response is going to be a Y. Okay, so that's going to be the observed behavior. We call this the target period, and sometimes we call Y the target variable. So the target variable or the target amount. Now, I'm going to use whatever information I have at the time the decision was made, which is right here, to make a forecast of Y. Okay, so I'm going to form a bunch of X variables using what's called the base period. So the base period is the period that happened before the decisions were made. So I form X variables like recency, frequency, and monetary. And then from this, I'm going to build some predictive model, call it F. And I evaluate F at these predictor variables in order to produce a score. Or you could also, think of, we've been calling those predicted values or Y hats. In scoring models, they get called scores. All right, so that's the idea of a scoring model. Now, the next question is, how do you evaluate a scoring model? So let me step back for a second and discuss what we've done. So our attention has been mostly on either accuracy metrics or decision support metrics. So what are accuracy metrics? They're things that are based on the residuals. So how far are my predictions from the observed values? And so things like R squared, the mean squared error, are summarizing the residuals and basically summarizing the accuracy of the model. Now, when it comes to a classification model, we just talked about many alternative metrics that get used for that case. And so those fall under the heading of decision support metrics. So these are things like what is the false positive rate? What is the true positive rate? What is precision, recall, F1, the area under the ROC curve would be another decision support metric. when it comes to these marketing models, we want to get closer to the thing we're actually trying to achieve. So marketers really aren't trying to achieve accurate predictions. They want to make money, right? So they want to generate responses and they want to generate revenue. So those are kind of the two things that marketers really care about. Now, usually when you have a model that fits well, you get these other things like responses and high revenues. But you can think about predictive accuracy is just a step along the way to getting to these true objectives. But we can create some accuracy measures that capture the real objective, which is generating responses and revenues. So the way these things get summarized is in a gains table. So maybe I've developed 2 or more scoring models and I want to determine which one is better. Well, the gains table is going to help me do that. So here are the steps in generating a gains table. The first thing I'm going to do is take the predicted values from my scoring model, which let's just call them y-hats, and basically I'm going to sort them from the highest score to the lowest score, so from best to worst. And so often the first 2 columns you're going to see, I've decided to put them into quintiles. In real life, we usually use more than quintiles. We might use deciles, which would be 10 groups, or demi-deciles, which would be 20 groups. So the prefix demi means half a decile, which would be 5%, so there would be 20 groups. But for the sake of the course packet, let's just use quintiles to keep the tables not so long. So what you're going to see is I've got about 10,500 observations in each one of these quintiles. And these quintiles then are just based on the predicted values. So this first row consists of the 20% of my database, so the 10,569 people with the highest scores. The next decile would be the next 10,569 people with the best scores. You're going to see that not all of them have exactly 10,569. And that's because, maybe our sample size doesn't divide by 5 equally, or maybe there's some tied values among these predicted values. So those could lead to not equal decile or quintile sizes, but don't worry about that. All right, next thing we're going to do is we're going to compute the number of responders, so we care about responders, and also the revenue that we generated in each group, each quintile. So this model is clearly doing something because in this first quintile, there were 1,681 out of the 10,569 in that decile that responded. Now that corresponds to about a 16% response rate. Now let's just compare that with the bottom quintile, which is the one that my model said is the worst. So these are like the worst customers according to my model. So in this group that also consists of 10,569 customers, notice I only got 159 responses, which is about a 1.5% response rate as opposed to a 16% response rate. All right, the next column just totals up the amount spent by those customers. So these 1,681 responders spent about $160,000. Now, if I divide $160,000 by 10,569, what that means is I'm getting about 15.1, so $15.10 per contacted customer in that first decile. So I send out the contact to all 10,500. I'm getting $15 per contact. So the bottom quintile, on the other hand, you'll see I'm only getting about $11,000 from them, which is about a little over $1 per customer. So you can think about this as a marginal revenue. If I go down an additional decile, how much do I expect to get from that decile group? So, mailing the second quintile, I keep saying decile, I mean quintile. So the second quintile, my revenue falls off pretty sharply. Go down to the next quintile, falls off even further. So this is short-term thinking, which is always dangerous. But let's just say all we cared about was revenue from this order. Let's say the offer cost me $3 to make. What becomes clear from looking at this table is I'm making money if I were to mail the first and the second quintiles, but notice I lose money on the third quintile. So I probably would not want to be contacting the third, the fourth, or the fifth quintile if the cost of the offer was $3. If the cost of the offer was $2, then clearly I'd still be making money on that third quintile, and I should go further and contact them as well. Now, I just mentioned that we probably don't want to just have short-term thinking. So this is a topic of another lecture, but there's additional value to getting a customer to respond. You have a better customer. They're recent, they're more frequent. And so even if I'm losing money in the short term, it can be a wise decision in the long run because I've made them better customers in the process. So sometimes you mail below the direct, the break-even point because you want to achieve some longer-term goals with the customers. But that's a topic for another lecture. All right, let's go over to the cumulative columns now. Let's now look at the right-hand side of this table. So the right-hand side of this consists of cumulative counts. So these are just running totals of what we're doing on the left-hand side. So let's say we wanted to mail or contact the first two quintiles. So in that case, we would add 10,569 in both the first and the second quintiles. That gives us a total of 21,000 people who've been contacted. All right. Now, we could also total up the number of responders we get. So notice if we add the 1681 in the first quintile to the 477 in the second one, we get about 2,100 responders. Now, if we divide the 2158 responders by the total number of those contacted in the first two quintiles, you get about a 10% response rate. So another way to think about that 10% is it's really just the average of these two response rates over here. So among the first quintile, I'm getting close to a 16% response rate. Among the second quintile, it drops to about 4.5%. The average of those two is about 10%. So 10% is about halfway between 4.5% and 16%. All right. We could also do this to revenue. So in the first quintile, we make about 160,000. Next one, we make about 40,000. The sum of those two's just under 200,000. So that's the total amount that I make if I were to contact the first two quintiles. Now, if I divide this by the total number of contacts made, so take 200,000 divided by 21,000, you're at about $9.45 per contact. So just as this response rate was an average of the two response rates of the first two quintiles, if I average $15.10 with $3.81, I get $9.45. So that's like the average amount that I'm making per contacted customer. Now I want to point out two very important numbers. These numbers are in the last row. So 5.35% is the response rate that you'd get from just picking names at random. If you mailed the whole database without any scoring model to help you, choose the names more judiciously, you're at a 5.35% response rate. Likewise, if I just pick names at random, I get $4.74 per customer, because the total amount of revenue generated was $250,000 divided by 52,000. On the average, you're getting just under $5 a customer. Okay, so think of these two numbers as the response rate and the average amount that you generate without a model. So I'm just picking names at random. Now, we often like to compare the amounts for other, depths. You can think of this as a depth. If I went two quintiles in, 40% of the names, that would be, a certain depth. All right. So what we end up doing is we divide the 16. Let's just take this 16% response rate, divide by the 15.35, and we get what's called the lift. So the way to think about this is the response rate that I get in this first quintile is nearly 3 times the response rate that I would get without a model. Okay, so this model is really doing a lot. It's really separating out the best customers from the not so good customers. Likewise, instead of generating $4.74, I make $15 per customer, which is over 3 times as much. So we could interpret the second decile in the same way, where you can see that instead of getting a 10% cumulative response rate, instead of getting a 5.35% response rate, using my model, I'm up to 10%. And so that's almost double the response rate. And likewise, I'm doubling my money generated per customer. So when we compare models, let's go back to my original question. Which model is better? We're going to compare models based on these cumulative response rates and amounts, or equivalently lifts. Lift is just a constant times the cumulative response rates and amounts. We're going to be comparing these values for where we think we're going to be using the model in practice. So if you think you're going to be separating this into, just taking the top 40% of the bids, then this would be a relevant number to compare. So I think we need an example of this. So let's go back to our DMEF3 retail data set that we discussed back in I guess it was week 2 or so of the class. I've written some dplyr code and put it in an R function to compute gains tables. So you can just copy this and paste it into R, and you can make your own gains tables. I'm going to let you read through that on your own. Let's go fit a couple models. So the first model I'm going to fit is a basic RFM model. And so this RFM model will regress whether or not you buy from recency, frequency, and monetary with a basic logistic regression model. Then what I'm going to do is put all of my variables into a model. So there were about 20 some odd predictor variables. And the question is, do I do better with this model that has 20 some predictors versus the model that only has RFM in it? Well, what I've done now is we can call up my gains macro, and this, don't call it a macro, a function. You give it the predicted values, you give it the true values for whether or not the customer bought, and you give it the true spend amount, so target amount. And this all goes into your call to the gains table. And what you should note is that you're doing much, much better with all 20 variables in there. So notice this gains table is actually the one I was just talking about on the previous slide, but this is the raw R output from my function. If you were to use the model with 20 some variables, you're generating $15.10 per customer in the first decile versus 11. So your revenue would shoot up from 116,000 to 159,000 just because you included more variables in the model. Now, if you went deeper into the mailing or into the contacts, let's say we go 40% in, the results are less dramatic, but still substantial. So 172,000 versus $199,000 in revenue. So it's like you're making what is that, $27,000 just because you had a better regression model. Likewise, the response rates shoot up. You're getting about an additional 1.5% to respond using the more sophisticated model versus the weaker model. Now, if I use my weak model to predict, to sort all the names, notice I make $4.74, which is what I make with my smarter model. So the smarter model doesn't help you if you're just going to go if you're just going to contact everybody. You don't need a fancy model. The fancy model is going to help you if you're only going to try to identify the better customers. So 2-3 deciles in, the differences are substantial between these two models. Now, another thing that we could do with my little gains function is to create something like an ROC curve. Now, instead of just having quintiles, this last argument to my function says, well, give me 20 groups, so demi-deciles. So by default, the number of groups is 5. I'm saying give me 20 groups. And so now I'm going to have a gains table with 20 rows in it. We could create some plots. And so these are very similar to an ROC curve. So on the horizontal axis, I've decided to put the number of people contacted. So this is like how far are you going into the file? And you could look at how many responders do you get, or how much revenue do you generate. Curves are pretty similar. And one thing to note is that random is what appears to be a 45-degree line. It's not really a 45-degree line because in an ROC curve, this would be 0 to 1 and 0 to 1. The scaling's a bit different, but it appears to be that 45-degree line. And so notice the way I've generated this is it's just this bottom row here. So for every additional person I send, I expect $4.74 to come back. And so the slope of this green line is $4.74. Likewise, there's a 5% chance that anybody responds. So the slope of this line would be about 5%. We don't really care about random. Random is not hard to beat. What we really care about is our two models. So this would be the RFM model versus the model with all of the variables in there. And notice how many more responders we generate for a given level. So this would be about the first quintile. If I go about 10,000 customers in, I generate way more responders with the red model than the black model. Likewise, I generate way more revenue with the red model versus the black model. So when I said, in comparing models, we want to use these cumulative amounts or cumulative response rates, that's what these graphs are showing. So just mention, in practice, you're going to have a lot of decisions to make where, do I use a logistic regression or do I use a neural network? Well, you would create graphs like this and choose the model that's better. Now, before before I close, I want to mention a couple things. The first thing is we really should be doing this on a test set. You know, just as I gave you a lecture earlier this week about how RMSE or classification rates or AUC, any of those other metrics that are computed on the training data tend to be optimistic. We have exactly the same problem with gains tables. So how could we generate, you know, an honest gains table? You could call this an honest gains table. Well, we do it exactly the way we did it before. So let's make a variable in our data set that randomly assigns cases to a training set or a test set. Then, as before, I'm going to give a subset command to say, when I fit the model, only use the training set. And so what you're going to see is instead of using 52,000 odd cases, now we're only using you know, about 11,000 cases instead of the entire data set. Okay, so I think we've been successful in training our model using only the training set. Then what do? Well, I've got to use the predict function to score my test set. So let's use not the training data, and then type equals response gives me predicted probabilities instead of the you know, eta values. And so we don't really need this for making a gains table, because gains tables just sort from best to worst. But we're going to need this on the next slide. So let's get predicted probabilities as opposed to the predicted eta values, the linear predictors. All right. So notice these p hats are all between 0 and 1. These are predicted probabilities. And we can make our gains table using the not training set, otherwise known as the test set. And so now we have an honest gains table as opposed to an optimistic one based on the training data. Okay, I'm going to mention one more thing that we went over with the retailing case, which is the notion of a two-step model. So the problem that most of these marketing models have is that the vast majority of people are non-responders. So I ran a histogram. We looked at this back when we did the retail case, week 1 or 2, whenever it was. And, you know, it was like 95% of the people don't spend anything, and then only 5% respond. If you're looking at something like click-through rates on a banner ad, the response rates are even lower. So one thing that's often done is to build what's called a response model with a logistic regression model. So I predict respond versus not respond with a logistic regression. So I separate the zeros from the positive values with the response model. Then I build what's called the conditional demand model, which is I want to predict the dollar amount spent. What's key here is for only those who responded. So if you respond, what do you spend is basically what the conditional demand model estimates. Then what I do is I compute the expected spend as follows. So among the people who don't spend anything, I make 0. So that whole term is 0. Don't really need it, but it's part of the formula for finding the expected value of a discrete random variable, in this case buy or not buy. Okay, plus here's the probability that you buy times the expected value of your spend given you buy. Okay, so think of this as the predicted probability from the logistic regression times the expected spend from the conditional demand model. Now there's an article that I linked to here if you want to read more about these and further refinements. This is often a way to improve the model. So how would you do this in R? Well, let's go fit our conditional demand model. So here's the conditional demand model. I call it fit.spend. We're going to use an LM now, and I'm going to regress the log of the target amount variable, say on RFM, but I'm only going to use cases that are both in my training set and where the person bought. All right, so this is a conditional demand model. What you'll see in this is recency has no effect. That's not unusual. Recency doesn't tell me how much you're going to spend. It tells me a lot about whether you'll buy, but it doesn't tell me how much you'll spend. Very often you're going to see something like frequency with a negative effect, monetary with a big positive effect. Now both of these have been logged, and let me just kind of explain why that is. So if we go over to the document camera, basically what we have here is log spend is equal to, let's say that the two coefficients were about the same, but of opposite sign. So let's say this is minus beta times the log of frequency plus beta times the log of monetary. All right, forget recency for now. But there's a property of logarithms that just says this is equal to plus beta times the log of, okay, monetary over frequency. And we can think of this as the average order amount. So if I take the total amount that you've spent in the past, divide by the number of orders, I get the average order amount. And so whenever these, that's why frequency often has a negative slope that's roughly the same magnitude as the monetary one, because when you have these log scales, it's really computing an average order amount, which you could include directly. All right, so let's now compute our predicted values. So I'm going to take the p-hats, which have to be predicted probabilities now. So make sure you've not forgotten your type equals response argument from 2 slides ago. That's one of the most common mistakes, and it's really embarrassing when you make that mistake. I've made it before, and you don't want to do that. So this is just p hat times, this is my y hat. Now I've logged y, so I have to exponentiate it. And so what I'm really doing is just computing this term. This is my y hat times the p hat. And then we can go, we could look at our gains tables, or we could look at our gains charts. I decided to make some charts here, and I didn't give you the code. Just take the code I had before and use it. And so the conclusion here is there's not much of a difference between these two models. So in this case, doing the two-step model did not help me much. Didn't help me in either case. You wouldn't expect it to help you find responders at all, but doesn't help you with revenue at all. And so in my experience, you will often get a small improvement with the two-step, but not necessarily a big one. But it's when you're making so many marketing contact decisions, even small improvements add up. Okay, so that's it for scoring models and how to evaluate them.